Hello, everyone. Great to have this opportunity to present our work. And my name is Peike. I'm a PhD student at University of Technology Sydney, and Professor Yi Yang and Professor Yunchao Wei are my academic supervisors. And today I'm going to talk about our work, Meta Parsing Network, towards generalized few-shot scene parsing with adaptive metric learning. Which we aim to make the segmentation model well generalized to a newly emerging open visual concepts with a little annotation labor. Semantic segmentation is broadly applied in the field of autonomous driving, video analysis, and virtual realities. The right video here well shows what semantic segmentation is, and which means each pixel in the image is assigned to a label like roads, car, or pedestrian, and so on. Currently, many promising architecture based on fully convolutional networks are proposed, like the FCN or PSP-NET or the famous Deep Lab series. However, the success of this advanced architecture highly relies on a large number of training images with pixel-level annotations. We know that it's quite expensive to obtain these annotations. And moreover, the current semantic segmentation scheme is usually based on closed set labels. And all categories are predefined before training, which means it leads to the learned segmentation model cannot generalize to some novel concept. So to tackle this issue and enable the segmentation model to equip with good generalization ability to some unseen categories, and meta-learning provides some promising solutions. In general, meta-learning, also known as the learning to learn, targets on learning new concepts or skills, adapts fast with some new training samples. Okay, this slide shows some of the conventional few-shot segmentation does here. And a standard setting of the current few-shot segmentation usually follows here. We feed one support image and one query image into the network simultaneously. And we aim to segment the query image using the support image as guidance. So although some impressive progress is made, and current explorations are only solving segmentation, which just aim on some simple objects, which usually one or two categories, instead of scene parsing with a full image. So in our work, we make one step further, and we advance the few-shot segmentation paradigm towards a more challenging yet general scenario. We call it the generalized few-shot scene parsing. Here is a difference here. You can see this is the image of our task compared to the conventional few-shot segmentation task. Our task aims to segment complex scene scenario with usually have multiple visual categories, and both seen and unseen categories are simultaneously considered. So during the meta training stage, we first train on the meta parser with annotated image on scene categories, and it's colored in green in the picture. And during the meta testing stage, given only one annotation image as guidance, the learned meta parser is applied to segment both seen and unseen categories. Here, our mission here is first we need to learn a very robust segmentation network. The second is that we need to both segment seen and unseen categories. And the third is that we need to learn a very fast adaptation ability and a very good generalization ability. And here we encountered two main challenges here. The first is we need to learn how to generate discriminative prototypes. And the second is we need to have a very strong generalization ability to multiple categories. And here is what we did in our paper. This is a framework of our method here, and we call it MPNet. It's a very robust segmentation network, and we learn it from meta-learning perspective, and which this network can generalize to both seen and unseen categories. And there are two main modules in our network. We call it a CID module, and it's the contrastive interclass distraction module, and the adaptive deep metric learning module, We call it the ADML for short. Let's go into some details. The ADM module aims to learn a transferable deep metric for dense comparison between the support and query image. To be specific, the ADM module is responsible for modeling the relationship between the pixels in the query image and the annotated one in the support image. So we adaptively leverage the non-local operations to generate the discriminative prototypes of each categories within the support image, and is further learned to learn a deep metric comparison between the query images. So we have the ability to tell each pixel in the query image what is the label of it. And the CID module is introduced to conduct the contrastive learning. And in this way, our MPNet will impose to produce some class-sensitive feature representations and resulting in a better generalizability to both scene and unseen categories. And here is some of the detail of our method here. Unlike some other methods, which usually use some like the average class-wire average pooling, which it does in some other previous work, it usually lost the feature diversity. We think it's not good. So in our work, we propose the adaptive prototype generation. And by doing this, we can exploit the rich diversity informations among all the pixels. And this is the dynamic installation of the multiple categories. And unlike some other methods, they do the comparison using a fixed metric, usually a cosine or L2 or L1, something like that. We automatically learn a deep metric for the comparisons. And our network can fast adapt to with very class-sensitive feature embeddings. And this is the training loss of our target here. Forget about the math here. What we did is actually we want to enlarge the interclass distance, and it's inspired by the MMD distance. Okay, as this is a new task for the generalized few-shot scene parsing, so we built two newly proposed benchmarks based on the cityscape dataset and the Pascal context dataset. And we divide all categories into seen and unseen split, and we mask all the unseen categories during meta training. So these unseen categories are never seen during trainings, and then we evaluate all categories, both seen and unseen, during the meta testing stage. And to ensure the fair comparisons, all results are reported by averaging 5 runs, and we report the MMU metric, which is a common metric in segmentation task. Here are some baseline models we used here. One is the Semantic network, which used the L1 similarity metric, and second one is a prototype network, which used a cosine metric, and also the state-of-art method called PNet. And our MPNet achieved the best result compared to all the previous method. And you can refer to my papers for more details about that. And we additionally answer 2 more questions. Here is one. Only given one question is that does multiple support image benefits? Here we conduct experiments from 1 shot to 10 shot, which means we have 10 images in the support set. We could see that with more support images, our performance continuously boosting. And the second question here is we want to the MPNet answer, does the MPNet generalize across domains? Also here we conduct experiment from the Pascal context dataset to the cityscape dataset. And our MPNet still achieved the best performance. Here we show some visualization result here. And you could compare the ground truth inquiry set with the MPNet, our network's output here. The green colors here is a seen categories, and the blue colors are the unseen categories. Okay, all right, conclusion here. In this work, we first proposed a new task. It's called the Generalized Few-shot Scene Parsing. And we proposed an MPNet. Our MPNet could generalize to some newly emerging open visual concepts with little annotation labor. And our MPNet induced the learned meta parser with good generalizability for complex scenario. And also there's still a large performance gap between the scene and unseen categories. So there still requires more effective meta-learning algorithm to do about that. Okay, thank you for your listening. And if you have some other questions, you could ask me.
Yeah, you can ask the questions by typing your question in chat or raise a blue hand here. Okay. Or you can unmute yourself to ask a questions. Okay, there's a question from Yinghua. Can you explain more why your methods works well in more complex problem settings with more categories?
Okay, great. Can you see my slides right now?
Okay, no. Can you share your screen again?
Okay, wait a minute. Yeah, here's what conventional Fewshot segmentation does. Usually only have one or two categories. And what we does here is we want to parse the whole images, which usually has multiple categories. And the conventional one, it was conducted on the seen categories and testing only on the unseen categories. And in our case, we are training on the seen categories and testing on both seen and unseen categories. And for here the question, how we deal with multiple categories here. One difference here is that we simultaneously consider all the categories together by the CID module, and which is enlarge the distance between the center of each prototype of each categories. And the second thing is that we parse the multiple categories not one by one. We just parse it together. So it's more suitable to our method, our task here. Yeah, I hope this answers your question.
So can I ask, is it based on the contrastive loss? You can have more fine-grained discrimination for multiple segment here.
You mean in the CID module?
Yeah, in the CID modules. Is it the key components for your methods to achieve the results?
It's not the key components. It's just some supplementary one. Yeah. So our key components is the ADML one.
Yeah. So do you have any additional study to show the ADML is the most important one?
Yeah. We have the result in the paper, so I didn't put it in the slides here.
Yeah. So, but for me, it's similar to do non-local legwork with some elder-in to do some instance normalizations.
Yeah, this is the nonlocal here is just we want to explore the diversity between the pixels. If we just average pulling maybe one category into a one prototype, so it lost the diversities between those pixels.
Also, may I ask which component in this ADML can consider this diversity on pixels?
Here is it's in the right one, the adaptive prototype generation here. Yeah.
Or do you have any detail on this? Because it seems you didn't explain this in details.
Yeah, it's details here. It's just inspired by the nonlocal operation here.
Oh.
And it's for the conventional method, they just use average polling to achieve only one prototype for the one category. Here we consider all the pixels together and to discover the rich diversity information.
Yeah, so my understanding is non-local level is trying to using some similarity to search similar pixels to do aggregations. So I don't know how can you using non-local level to achieve the diversities or for your problems. Yeah.
It's like if you know, let me put it straight. If you just use the average polling, so each pixel contributes equally to the final prototype. But in our network here, each pixel automatically learns a weight. That's the main difference here.
Okay, I understand. Yeah. So basically using non-local network to define the weight for different pixels.
Yeah.
Okay. Any further question from other audience? Okay, so anyone have further questions? Why you choose MMD in slide 12?
Why do I choose MMD? Right, in the SID module, right?
In the slide 12, yes.
Here is you can have some alternatives here. If you can just simply use cross entropy here, but what we want to tell is that if you use cross entropy, so that is related to the class numbers. So, but if we use the MMD model, it's not related to the categories. So we can expand multiple categories easily. It's in one word, it's a non-parametric method, loss method. But if we use cross entropy, it's a parametric based. That's the main difference here.
Okay. Any further questions? Want to ask the speaker? Maybe time. Okay, so if no, then we can come to the last talk for these sessions. Thanks, speaker.